section 2.4, infinite limits. Infinite limits. In this section, we will learn about infinite limits. This occurs when a function values increase or decrease without bound with near a point. All right, so to begin, let's talk about two phrases that sound very, very similar. Infinite limit and limit to infinity. Let's talk about one example of an infinite limit. So let us consider just the example of f of x equals 1 over x squared. If we ask what is the limit as x is approaching 0 of 1 over x squared, we would say that it continues on to infinity. We see that at 0, if we look at our graph, we pick numbers that are closer and closer to 0. As our numbers get closer to 0, our numbers get really, really big. So we would say that as we get closer to 0, it's approaching infinity. Or we can look at our graph and we see that at 0, well, there isn't really a point, but these graphs are continuing on forever at a positive value. So we would just say positive infinity. So this is an infinite limit. Not to be confused with limit to infinity, which is what we'll cover in our next section. It can be commonly confused with infinite limit, but there are considering the x values continuing on forever to infinity. So we can propose a function above as the limit as x is approaching infinity of 1 over x squared. So we see by the sketch below that we're not saying if it's approaching a number, we're approaching infinity. So we're looking at the x values to the positive side and the x values to the negative side. And we see that as our graph continues on for x values, what is it approaching? It's getting closer and closer and closer to 0, but never touching it. Same thing for this other side. As we go on to negatives, it gets closer and closer and closer to 0, but never touches. So we say that the limit as x is approaching negative infinity of 1 over x squared is 0, and the limit as x is approaching infinity of 1 over x squared is 0. And this is our next section, so this will be what we'll talk about in 2.5. Okay, our focus in this section was that first example, or infinite limits. Definition of infinite limits. So there's three things to consider. A. Suppose f is defined for all x near A. If f of x grows arbitrarily large for all x sufficiently close but not equal to A, we write that the limit as x is approaching A of f of x is equal to infinity. And we say the limit of f of x as x is approaching A is infinity. Or B, if f of x is negative and grows arbitrarily large in magnitude for all x sufficiently close but not equal to A, we write that f of x equals negative infinity. In both cases, if it goes from negative infinity and positive infinity, the limit does not exist. Remember, they need to be approaching the same area, the same value for it to be considered a limit. So here we see that first part where we see that as it's approaching a number, it's getting larger and larger and larger and larger. So we say the limit's approaching infinity. And we see that it's not just happening from the right side, positive side, but it's also happening from the negative side, the left. Same thing for this other graph, B, but now we see that it's continuing on towards downward, larger and larger negative values. So we say that it's approaching negative infinity. As you can see, the left side and the right side are both going towards that negative infinity. There is a case, and we'll see this like C, where one graph goes towards positive infinity and the other side goes to negative infinity. In such case, we would say that at that value, the limit would not exist because they don't go the same way. Let's take a look at an example. Analyze the limit of x approaching 1 of x over x squared minus 1 squared, and the limit of negative 1 of x over x minus 1 squared using the graph of the function. Okay, so we're just going to take the pictures so we can go take a look at the pictures so we can go ahead and be able to understand how these limits are working. So this first part is saying that we're trying to see what's happening at 1, positive 1. So if we take a look at our graph, and we see here that at 1, this is 1, both the right-hand side and the left-hand side are both approaching upward forever. So they're both going towards infinity. So for the first one, we would say that the limit as x is approaching 1 of x over x squared minus 1 squared is equal to infinity. It goes on forever. Okay, now let's take a look at our other question. Let's take a look at the same function, but now we're going to consider when our graph is approaching negative infinity. What's going on then? Well, not negative infinity, negative 1. All right, so we find negative 1 in our graph, and we see that both from the left-hand side and from the right-hand side, they're both approaching downward, and it gets bigger and bigger, a larger and larger negative number. So they're continuing on to negative infinity. So along with the same reasoning, for this one we would say that it would equal negative infinity. And again, all these images and all these examples are from your textbook. So if you want to read more or just see different phrasing, different wording, I invite you to check out your book. Definition of one-sided limits. Suppose f is defined for all x near a with x greater than a. If f of x becomes arbitrarily large for all x sufficiently close to a with x greater than a, we write the limit as x approaching a from the right side of f of x equals infinity. The one-sided limits limit as x is approaching a from the right side of f of x equals negative infinity, and the limit as x approaching a from the negative side of f of x equals infinity, and the limit as x approaching a from the left of f of x equals negative infinity are defined analogously. So it's just telling you all the possible ways that you can have a one-sided limit. So you can come into the right and go forever positive to infinity. So as a from the positive, you can have as x approaching from the positive and get a negative infinity because it's going downwards. So we would say as x is approaching a to the positive side, our limit is negative infinity. And same arguments from the left. So we see as it's going on from the negatives, we go to positive infinity, just like we see here. It goes on from the negative onto negative infinity, just like it says here. Definition of a vertical asymptote. A vertical asymptote is defined as if the limit as x is approaching a of f of x equals positive and negative infinity, and the limit as x approaching a from the right of f of x equals positive or negative infinity. Or the limit as x approaching a from the left of f of x equals positive or negative infinity. The line x equals a is called a vertical asymptote of f. So just to help you recall from, I don't know, your algebra days or your pre-calculus days, when you have a vertical asymptote, You have vertical asymptote. That happens when you set your denominator equal to 0. Remember, that's where you know you're going to have an invisible vertical line that your graph will not cross, ever. There's no exceptions to vertical asymptotes. Let's go ahead and take a look at this example. The vertical lines x equals 1 and x equals 3 are vertical asymptotes of the function f of x equals x minus 2 over x minus 1 squared and x minus 3. Use the image to analyze the following limits. So far we're just looking at graphs and making sure we understand how these infinities equaling infinity and negative infinity come to be. So we're looking at our graph, and we see that just like our note said, we have asymptotes at 1 and at 3. So those are lines that our graph will not cross. It will get really, really close to, but never cross or touch. And we see everything that our graph has to offer. Let's take a look at our examples, our questions from our example. For A, it's asking the limit as x approaching 1 of our function. All right, so we just take a look at 1. At 1, what's happening? Well, I see both parts of my graph are continuing on to the positive side, to positive infinity. So our first answer is the limit as x approaching 1 of g of x is going to equal infinity. So our little reasoning, both lines or both parts of our graph so our answer would be the limit as x approaching 1 of g of x equals infinity. Now we see there's a little typo. I should have a little plus right here for C. All right, now for B, it's saying the limit as x is approaching 3 from the left of g of x. Okay, so as I look from the left side, I see that my graph is going downward. So my answer would be the limit as x is approaching 3 to the left of g of x equals negative infinity. And for C, we see our graph, and from the right hand side, we're coming in from the right, and it keeps going up, 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 up at 3. So because of this, we say that our limit as x is approaching 3 from the right of our function g of x, our answer is infinity. So if there were a third question saying, so let's add our third question. What is the limit as x is approaching 3 of g of x? Well, we have just shown how the infinity from the left is negative, and the limit from the right is positive infinity. These limits are not the same. So we would say our limit does not exist. Finding infinite limits analytically. In the example we have above, we have been able to find the limit using the graph of the function. Now we will learn how to approach it differently, how to go without a graph, how to, in a sense, do it algebraically. Okay, so let's take a look at this example A. Find the limit as x is approaching 3 from the right of 2 minus 5x over x minus 3. So our problem here is that I can't plug in 3 because it gives me a 0 in the denominator. Right? And that's our problem. It makes it undefined. So how can we take a look at our graph coming from the right? All right, well, we see that I can't pick 3, but, so for this, I could draw a quick little number line. I can't pick 3, but I can pick a number that's maybe slightly larger. How about 3.1? So what happens when we plug in that 3.1 in the denominator? So let's plug in 3 in our numerator since that's okay. We have 2 minus 5 times 3. And in our denominator, we're going to think about a really close number that is not 3. All right, in our numerator, we get negative 13, right? 2 minus 15, negative 13. In our denominator, we're plugging in 3, but we're mentally trying a number that's slightly bigger than 3 because we have a plus. So in your mind, think 3.1, but really we want 3. So we know at 3 it's 0, but if we think of a number that's coming in from the right, it's going to be 0 and positive. Because just this is what we're thinking in the back of our head. 3.1 minus 3. And if I pick any number that's smaller but closer to 3 but not quite, it will be just slightly bigger, so we'll get positive. That's why we say 0 and positive. All right, so now we think of our fraction. Our fraction is made up of a negative and a positive. So our outcome, I know I have an asymptote there, but we know our outcome should be a negative. Therefore, our answer is negative infinity. Pretty sneaky, right? Let's take a look at 3 from the left. So we're taking our same graph and we're going to look at it from the negative from the left. So we're going to do the same thing. We know we can't pick 3. It's going to give us a 0 in the denominator. But I can pick a number that's really close to 3 because it's approaching from the left. So again, if you draw a number line, I can't pick 3, but I can pick a number that's slightly smaller since it's from the left. So what about 2.9999, for example? Okay, let's work this out. So I have 2 minus 5 times 3, since we're working with 3, divided by 3 minus 3. In my numerator, we get the same result. 2 minus 15, we get negative 13. And in my denominator, what if instead of 3, I think of a number that's slightly smaller since we're coming in from the left? A number that's slightly smaller. Then we'll have something like 2.9 minus 3. That will result in a negative and 0. So because our fraction is made up of a negative and a negative, our answer, well, what's a negative divided by a negative? It'd be positive. Therefore, our answer is positive infinity. Let's do another example. Analyze the limit as x approaching negative 4 from the positive. Okay, so we're trying to see what happens at negative 4. Before you even start, whenever you have a rational function, always try to factor to see if it can be simplified in any way. All right, so let's go ahead and go through our factoring trouble. Factoring. Let's factor our numerator. So for our numerator, I have negative x cubed plus 5x squared minus 6x. Okay, I can factor a negative x, and I'm left with x squared plus 5x minus 6. That's a trinomial with our leading coefficient being 1. So what numbers multiply to be negative 6 but add to be 5? Negative 3 and negative 2 work. So that factors to be negative x times x minus 3, x minus 2. My denominator, well, that factors to be negative x cubed minus 4x squared. I can factor out a negative x squared, a GCF, and a greatest common factor, and I'm left with x minus 4. Okay, so we put this together. Our new graph, or our new function is negative x times x minus 3 times x minus 2 divided by negative x squared times x minus 4. All right, and we see that we can factor out a negative, an x, making this x to the first power. And that's about it. All right, so now we have our new simplified fraction that gives us x minus 2 times x minus 3 divided by x times x minus plus 4. Okay, so now I want to think about the same thing. I'm working with this limit as x is approaching negative 4 from the positive. So I know I can't plug in negative 4 in my denominator. It'll make this 0, and that's the problem. So for that particular one, in my head, I'll think of a number that is slightly bigger than 4, negative 4. Okay, for the rest, let's go ahead and plug in 4. If I plug in 4, negative 4, I'm left with negative 4 minus 2 times negative 4 minus 3. We're left with 42. And if I plug in a slightly bigger negative from the right, so like negative 0.39. So let me draw a number line. I can't use negative 4, but I can use a number that's slightly bigger from the right. So negative 3.9, for example. If I do that, I'm left with negative 3.9 plus 4. This will give me a positive. Negative 3.9, that's a negative. So if I multiply them, I'll end up with a negative. So I have to think, what is my fraction going to be? In my numerator, I'll have a positive, and in my denominator, I'll have a negative, thus resulting in a negative answer. So I know I'll be an infinity because it's an asymptote, but we can say that it's approaching negative infinity. And I saved the trouble of graphing it, but we're using technology here, right? So you can be using a graphing calculator or your Desmos graphing calculator. Don't try, if you can save time, do it. Use technology. Let's take a look at another example. Let f of x equal x squared minus 4x plus 3 over x squared minus 1. Determine the following limits of the vertical asymptote of f. Verify your work with a graphing utility. For example, a graphing calculator or Desmos. So before we start, when you have a rational function, you always want to try to simplify, try to factor it, see what happens. So as we're taking a look at this, I see we can factor our numerator. So what numbers multiply give you 3 that add to give you negative 4, negative 3, and 1. So my numerator is x minus 3, x minus 1. And my denominator, we see that's a difference of squares. That factors to be x plus 1, x minus 1. And we see, ooh, that's a value that I can disregard. Do you remember what happens when I have a factor that can be divided to make 1? In a rational function, when this happens, it creates a hole in your graph, meaning it's just a single value that makes it not true. So when we graph it, all we do is at that value, we write an open circle to represent that value that isn't a part of our function. That makes it undefined. All right, so let's verify these limits. The limit as x approaching 1, well, I can go ahead and use my simplified version. And we just saw that it equals x minus 3 over x plus 1. If I plug in a 1, 1 minus 3, and 1 plus 1, we get negative 2 over 2 to equal negative 1. So our answer would be the limit as x is approaching 1 of f of x equals negative 1. Cool beans. What about negative 1? So negative 1 isn't something I can work with because in our simplified graph, x minus 3 over x plus 1, if I plug in a negative 1, we get 0 on the bottom. So that gives the problem. Okay, so now I have to consider what happens at negative 1. Is it a positive answer or a negative answer? What's going on? So if I plug in a negative 1, negative 1 minus 3, we get negative 4. If I plug in a negative 1, well, I can't. So I pick a number that, well, it's coming from the left. So I like to always draw my number line. If it's coming from the left, I want a number that's slightly bigger. I'm sorry, slightly smaller. So like negative 1.01. Okay, if I do that, I'm left with a negative. Negative 1.01 plus 1, I'm just left with a 0.01. So this would give me a negative and 0. So my answer would be, well, I have a negative divided by a negative, that gives us positive infinity. All right, let's do the same thing, but now consider from the right, positive numbers. Not positive numbers, numbers that are very, very slightly bigger. So I have x minus 3 over x plus 1. If I plug in a negative 1, well, where we saw, we'll get negative 4. Now here, we are approaching negative 1 from the right side. So let's try negative 1.0001. No, negative, have to be careful, 0.999. There we go. So if I have negative 0.99 plus 0, this will give me in the denominator a positive number because my negative will be slightly smaller than my positive one. So when we add them, we'll get a sum that's positive. So I'll have positive and 0. Now we have our fraction where we're taking a negative divided by a positive. We get a negative infinity. So we see our answer. We're able to come up with this. Now, the reason why it's mentioning our graphing utility is because sometimes it'll leave out these holes, but it shouldn't, you should still up with the same answer just as we saw, but it's just not giving your entire graph. So here we see our correct graph has our hole, and our calculator graph may not emphasize that single open value. But either way, also, it also wants to emphasize that our graphing utility may not emphasize that it's an asymptote as a dotted line. Because correctly, when we graph it, we go through the process of graphing a dotted line, so we visually see where the asymptote falls. But really, we don't need to draw anything. It's just an invisible line we don't cross. And we see that in a graphing utility, they might go through the process of drawing it like a whole line, which is not technically true. It's not a graph, it's just a portion of our graph. Okay, now our limits work the same way with trig functions. So we have cotangent of theta. If you don't remember too well how your trig functions look like, you can punch it into your Desmos graphing calculator or your graphing calculator. So just to remind you, we have cotangent of theta. Cotangent and tangent have asymptotes. since tangent is made up of sine over cosine, and thus cotangent is cosine over sine. So as we graph these values at pi over 2 and negative pi over 2, we have these branches, and these branches have asymptotes that do not cross. So if you recall, your branch for cosine looks something like this. These are your graphs of, not cosine, cotangent. And you have repeating dotted lines that are your asymptotes. However, we can still read it the same way. We can take a look at a graph coming from the left to the right and seeing if it gives us infinity or negative infinity. So let's take a look at this first question. A. The limit as theta approaches 0 from the right of cotangent. So 0 from the right, we see that our graph is going forever. 0 from the right, it's going forever up. So our answer would be infinity. What about 0 from the left, which is B? B is asking, find the limit of theta as theta approaches 0 from the left of cotangent theta. So to take a look at this from the left, from the negatives, our graph is approaching downward. So negative infinity. Our answer for that one would be it equals negative infinity. So just like our functions, we saw our rational functions, our trigonometric functions follow the same rules of limits that we established in this section. All right, that's it for section 2.4. Thanks.